Hey everyone, welcome to our talk today. Our speaker is Professor Christopher James. He is the director of the Biomedical Engineering Institute at the University of Warwick. Professor James received his PhD from the University of Canterbury, New Zealand in 1997. After briefly working in the semiconductor manufacturing industry, he was a postdoctoral research fellow at the EEG department of the Montreal Neurological Institute of McGill from 1997 to 1998. From 1998 to 2001, he was a postdoctoral researcher with the Neural Computing Research Group of Aston University in Birmingham, and until 2003 was a lecturer with that same group. After this, he was a reader in biomedical signal processing at the ISVR, University of Southampton. And then from 2010 until 2015, he was a professor of healthcare technology at the University of Warwick and director of the Institute of Digital Healthcare. He is now professor of biomedical engineering and director at Warwick Engineering in Biomedicine at the University of Warwick. His research interests include the analysis of EEG and magnetoencephalogram signals through intelligent signal and pattern processing techniques. He's also interested in the development of wearable technology for the assessment of behavior and behavior analysis techniques. He is further interested in the development of blind source separation and independent component analysis based techniques for practical implementation in multi-channel and single-channel biomedical signal recordings. He's a member of the IEEE Engineering in Medicine and Biology Society and was past Europe representative on the EMB Administrative Committee. He is chair of the UK and Republic of Ireland EMBS chapter and past IEEE 8 vice chair for technical activities. He's founding editor-in-chief of Healthcare Technology Letters with the IET. And we are very excited to have you with us today and let you take it from here. Talk title is Almost an Android.
Excellent. Thank you very much, Jonathan. And yeah, sorry for giving you a long list of things to read out. Today I thought, I'm not going to be too technical. I've chosen on purpose not to be too technical and to have an approach which is sort of a philosophical approach almost to BCI, sort of where are we, where can we be, and where is this going sort of thing. Hence, the sort of tongue-in-cheek title of Almost an Android. That picture there, that isn't me. That's a journalist of the Sunday Times, and that's my daughter. My daughter and my son feature a lot in my experiments and my videos. So let me get cracking straight away into this. Right. So I'm going to talk about what is BCI very, very briefly. And I'm going to talk about two different ways in which we can do BCI. One thing which I call self-paced BCI, brain to motion, and responses to stimuli BCI, or brain to text. After I've introduced those, I'll talk about a really nifty little experiment that I ran, which was almost a bit of fun, really, on brain-to-brain communication. And then finally, I'll finish off with a look towards the future. Where is this headed, and where could we be in BCI in the future, perhaps not in the too distant future? So what is neural engineering? I say I work in the neural engineering field, and essentially it's about using the methods that we learn about the brain and bringing them to bear on methodologies, but also at the same time, it's about learning about how the brain works. There's a bit of a symbiosis there, learning how the brain works and then using that information to do engineering, do bioengineering better. And so this is the sort of the gross area in which I work in neural engineering. And so what is BCI? I saw this picture a very long time ago, and I think I really love it. It's basically you have an individual trying to communicate with the outside world, and you're doing it through a computer, hence brain-computer interfacing. And you are doing it by thinking, by creating a mental image, activating parts of your brain. And we have EEG, or the electroencephalogram, the recordings of the electrical activity of the brain. We pick those up, and from an engineering perspective, we do some signal analysis and we interpret the brain signals, and then we do whatever it is that you want to do. This person is really desperate for a cup of tea, and the desperation and the sort of, if you like, the amount of energy going into make me a cup of tea, which is something which is a relatively simple act. In a way, I'm pretty sure the cartoonist didn't know this, but it does reflect a certain amount of intensity with which we have to do things at the moment to be able to get really nice, cool responses. So if we break down the process of BCI, or brain-computer interfacing, there are three basic things we need to talk about. And one very crucial observation is that essentially it's a closed loop system. In other words, the end user is creating a thought, whatever, we're picking it up and we're interpreting that thought, and then the end user visualizes the outcome and may or may not modify their behavior. So you have this circular dependency. And so we start with the data acquisition side of things. We somehow need to extract information from the end user. We then go on to processing that information and providing feedback. Now, let's start with the data acquisition. As it stands at the moment, we can either glue scalp electrodes, or electrodes placed on the scalp, or we can drill holes and put electrodes deeper into the brain, either on the cortex or deep into the brain. The number of channels in a normal scalp recording is around 19 channels. It can go up to about 256. The only limitation is physical space and the huge amount of time it takes to put these electrodes on. If you're dealing with implanted electrodes, you could have thousands of electrodes, but again, the square footage or the area that you're covering is going to be large, and of course you bear in mind we're drilling holes in people's skulls, so there's always sort of give and takes with these things. Now, we can do the data acquisition whether it's either a stimulus linked or a cognitive task, and I'll follow up on this in a few slides, but basically either the person is creating the mental image, or we're stimulating the person and looking for the response. So stimulus versus the cognitive task. So that's how we generate data. We then need to analyze the signal. And one thing that you realize very quickly is that you need to do this in real time. Because if you are controlling something, whether it's a wheelchair, you're putting the kettle on, or typing on a screen, you need to close that loop. And so the processing needs to happen quickly. The downside is we're dealing with very poor quality signals. EEG are in the orders of tens of microvolts, and the amount of other signals that we pick up, rubbish basically, is huge, and it masks the brain activity that we're interested in. And so it's a very tough struggle to extract signals which are useful. Now, of course, it is affected by the number of channels. If you have just one channel, one recording electrode, then you have a limited amount of information. On the flip side, if I had 1,000 channels, does it mean it's going to be any better? Not necessarily, because you have this sort of curse of dimensionality, and you end up with other issues that you have to deal with. So there's a sort of a balance point to achieve. And then the third item in my little feedback loop essentially is the user feedback. Now, is it going to be virtual, or is it going to be actual? In other words, are you going to see a bar moving on the screen, or is the wheelchair going to move? Also, is this going to be used routinely? So do you have an implant and you are depending on this implant to move the wheelchair that you're in? Or is this going to be used as a rehabilitation tool? You'll do it intensively for 2 weeks, and then you won't need it anymore. Now, clearly, the feedback and the type of system that we use for those two is different. And again, you'll see that it actually is very stimulus dependent, depending on the sort of feedback we give. And I'll talk about that in a few slides. So that gives you a bit of an overview of what needs to be in place for BCI. And essentially, the big question that you'll find yourself is this: do we use surface electrodes, i.e. scalp electrodes, or do we use implanted? And there's sort of pros and cons. I've listed a few there. There are others. If, for example, what you're doing is temporary, then drilling holes to put recording electrodes is not a good idea in a temporary situation. So if you're expecting recovery, you might use surface electrodes over implant. There's surgical risk with implant, and if the risk is too great, then implants may not be an option. If it's just the case of establishing a communication with someone for the first time, somebody who might be in a locked-in syndrome environment, it may well be that you would do this first, but then you'd do something else. Is it assisting movement, or is it the only means of movement or the only means of communication? And also, how flexible do you want this to be? In other words, today it might be about moving a wheelchair. Tomorrow it might be about moving a cursor on the screen or virtually typing. If you need to move electrodes around on the scalp, you just pull it off and move it along. If you want to look at a different part of the brain in an implant, you have to physically drill holes, insert electrodes with all of the issues, that brings with it. So basically, there's a very big, tough dilemma there. And essentially what it is, do you want to have what we have on the left, which is a socket sticking out of somebody's head where there's an implant? And this is from the quite famous BrainGate system in the US. Or do you have scalp electrodes? The worst thing that can happen is that they fall off and somebody else, glues them back on. And there are pros and cons. I won't go into whether we should use one or the other. Just be aware that they're both there, and we can do BCI using both, but with differing outcomes. So I've given you a very quick run through as to what is BCI. I'm going to talk now about one particular type of BCI, the so-called self-paced BCI, which I call brain to motion. Now, one of the nice things about being an academic is that you get people coming to talk to you to do interesting things. And I don't know how many people here know Top Gear, the BBC program. At the time, there was a number of personalities, one of them being this guy here, James May. And he came to me and said he wanted to move a wheelchair. He wanted to be able to use BCI to move a wheelchair with his brain. And he created a program, a documentary essentially, called James May's Big Ideas. And so the way the BBC does these things is they call you 2 weeks before and say, can we come and record? And I didn't have anything. So that basically they bought a wheelchair off eBay, dropped it off at my home. And I spent 2 weeks strapping my daughter to a wheelchair and, creating a system where you imagine moving and you translate, the computer translates that movement into a control signal for a wheelchair. And so the only sort of technical slide really that I'm going to show you is it's very simple. It really is when you think about it. If you sit and imagine moving, imagine doing this with your arm, but not actually doing it. So if you keep your arm down and imagine doing that with your arm, or imagine punching, or imagine swimming, that imagination creates a preemptive, if you like, activity over the motor cortex, because it's motor related. And in this particular example that you can see here, in the frequency spectrum of two electrodes on the left and on the right over the motor cortex, you can see a nice clear peak in around the sort of 12, 14 hertz, which is exactly around the frequency activity that we expect to see over the motor cortex. And you'll see that it's stronger on the left versus the right. So basically, if we just put electrodes over the motor cortex and we ask somebody, imagine doing this with your right hand, or imagine doing that with your left hand, we can tell when that imagined movement occurs. We do some very simple signal processing, extract the peak, and decide whether or not you were imagining a left-hand movement or a right-hand movement. And in fact, I was only using three recording channels here, 2 channels over the motor cortex and a reference. So I've got a video here, which is part of James May's Big Idea. And in this case, what he's doing, he's sort of practicing, and he's moving a cursor on the screen before he goes into the wheelchair. There's some audio with this. I think you should hear it, but if you don't, just let me know. Okay.
Okay, let's do one. Absolute concentration. Remember, it's cat stroke for left, face punch for right. Yes.
Well done.
That was a direct thought-controlled hit. Stage 1 complete. Time to wire me up to the Merc. That is the mind-enhanced roving chair.
So there you see James May talking about cat stroke for left and face punch for right. So that's his imagined movements. Now, in actual fact, he's a pianist, and what he was imagining was right-hand piano movement and left-hand piano movement. And that's not really very cool for TV. So whilst he was actually imagining something, he was saying that he was imagining something else. And that brings forward one of the problems that you have in BCI. Because yes, if you imagine moving your arm, if you imagine it, if you think of nothing else and do that, we can pick up a really strong signal. But if you're sitting in your wheelchair, imagining move right because you want to get out of the way of a bus, and you're really, really very scared and lots of things are happening, then that signal that we get, that we end up with, is really, really poor. And so basically, if you're not attending more or less 100% to that action, the outcomes can be very, very poor. And in actual fact, James May was really bad at doing this. However, my daughter, who was, like I say, strapped to a wheelchair after school for 2 weeks solid, she got very good at it. So they had a little bit of a competition going between James May and my daughter, who at the time was, I think she was 9. So if you move on to the next one. So there's my daughter. She's holding the laptop. The EEG amplifiers are on the back of the wheelchair. She's got a few electrodes on. And I'm just going to show you, there's no sound to this. All she's doing is imagining moving left and right. She's steering the wheelchair, but the wheelchair is moving forward on its own. So she can maneuver without crashing into a wall quite well. And you see right at the end there, my son goes forward and he switches the wheelchair off before she does crash into the wall, because she's only moving left and right. She can't start and stop. Yeah, and we can add start and stop, because you can say, imagine doing this for right, imagine doing that for left, imagine kicking a football for forward, and imagine jumping or swimming for backwards or stop or whatever. You can do that, and we can pick up signatures. But as before, what tends to happen is the performance starts to drop. So whilst we can do it, instead of having like a 90% success rate, we end up with something like a 50% success rate or a 60% success rate, which of course, if you're in a wheelchair, you don't want to be throwing a dice whether you're going to go left or right. Yeah. Now, bear in mind, we're only using scalp and we're only using 2 electrodes. So it's actually, pretty good achievement considering. So this is now her competing with James May.
Everything apart from stroking a cat or hitting a bloke in an annoying building society advert. You try it. Think of nothing else but those things. I'm useless at this. Now, I'm sure you'll agree I was rather brilliant at that, but I think it's time to up the ante with a thought-controlled wheelchair racing competition, for which I need an adversary, and I have one in the form of Gwyneth, who is 9, but she is also Christopher's daughter and has spent a great deal of time helping him with these sorts of experiments. So she's actually rather good at this sort of thing. In fact, unofficially, she is the British electric thought-controlled wheelchair racing champion, though possibly not for much longer. Are you up for a race?
Yes.
Good.
All we had to do was clock the quickest time to the finishing post.
Well done, you're the champ. This technology could have a very obvious application one day to the fields of medicine and mobility, but I'm not sure it's quite what I'm looking for my dumb robot problem. Because the whole point of me having, say, a domestic robot would be that I could send it off to do the washing up while I apply my giant brain to something more useful, such as watching Where Eagles Dare on the telly again.
So basically what James May highlights there is the fact that A, if you haven't trained a bit, you're not going to be very good, and he hadn't trained at all. And B, he's too busy talking to the camera and trying to come up with interesting, speech rather than concentrating on the job. And he was bouncing all over the place. He was going around in circles and crashing into walls. It really couldn't get anything interesting out of him. But my daughter, who had some practice and was concentrating on the task, etc., could do it quite well. And that shows you how you can do things, but the stars do have to align a bit for it to work perfectly. And in fact, people who've used BCI longer term will tell you that at a certain point, whereas you start off imagining doing this with one hand or this with another hand, you reach a certain point where you're no longer imagining doing that, but you're just willing the wheelchair to go right or willing the wheelchair to go left, because you've sort of learned whatever mechanism that you're using, to invoke the left and right. You've learned it, and you sort of jump that extra step of imagining doing an action. So there clearly is a feedback and a learning element to this. Okay, so here's now a picture of my son suspiciously sitting in the passenger side. This is the UK, in the passenger side of a car with wires coming off his head. And this was a few years later. Top Gear came to me and said they wanted to do a segment where they had two of their presenters racing cars using BCI. Now, if that wasn't a recipe for disaster, I don't know what wasn't. But thankfully, we were saved, because you may be aware that the whole Top Gear thing crashed when one of the Top Gear guys punched a producer and they all got sacked. And and this story got filmed but didn't get used. However, I do have some of the footage myself. So here we see my son. He's just got 3 electrodes, and the computer, which is, you can see somebody's holding it in the driving seat, is moving a servo to steer the car. So in this particular video, you'll see this. Essentially, it's a remote controlled car. The guy with the remote control basically has the emergency stop, and the car is rolling forward, and my son is steering it, and all he has to do is drive it around the car park without hitting anything. So no real slalom or anything like that. Just don't hit anything. And you see that, he can steer it. We're moving very slowly. But, he can steer it, and we can do a relatively good job. But again, are we ready yet to have people driving cars through BCI at this stage? Clearly, we're not. However, extremely, extremely positive, because, we've shown the proof of concept, if you like. Okay, so this is the brain to motion side of things. Now I'm going to skip
Christopher,
Yep.
In that experiment, and I guess the wheelchair one too, they're just guiding directionality. They're not doing sort of an accelerate, decelerate.
Steering only.
Action.
They're only steering.
Okay.
Yeah. Like I say, we could add a third channel where we add acceleration, etc. But the whole performance generally drops. So yeah, we can do it. It can be done. Yeah. So now I'm going to go to another type of BCI, where instead of the user self-initiating, self-pacing the response, it's a bit easier, because basically we present a stimulus to the user and we observe the response of the brain. So let's call it brain to text. And I call that because there's something called the so-called brain speller, or the P300 based BCI. And basically, the way this works is you have a screen in front of you, and with the alphabet, as you can see there, and the rows and columns are randomly flashing. And if, let's say, you want to type the letter O, all you have to do is just look at the letter O. And what happens is, because the rows and columns are randomly flashing, when the letter O happens to flash when you're looking at it, the brain generates something called like a recognition response. It's called a P300 response. In fact, P300 means a positive peak 300 milliseconds after the stimulus onset. And it's a very clear, again, within certain confines, it's a very well-defined response. So basically, all we need to do is, for every row and column that is flashed, once they've all been flashed at least once, we look for the two responses which line up with a row and a column, and through triangulation, we can basically say, you must have been looking at the character O, because when that row and that column lit up, we got a response. And that's it. We can tell that you were looking at the character O. And it's a bit easier type of BCI, because all you need to do is just look at the character rather than conjuring up any sort of mental images, if you like. So the way it works is, again, the P300 is strongest on the central part of the cortex. Again, so if you're looking at the letter I, every time the letter flashes, we get a response. And so the sort of response looks like that. You get a nice peak when the row or column flashes, and you don't get a peak anywhere else. However, unfortunately, you don't get a nice strong response like that. The response basically builds up if we repeat the experiment. So what you do is you flash all of the rows and columns a number of times, say 15 times, and you get an average basically of 15 responses. And then you get a really nice strong response. And you can basically type just by looking at the characters. And the sort of things that we're looking for on the left, we're looking at the activity from electrode CZ, which is sitting right in the center, for processed, cleaned up EEG. The red are the target, in other words, when you were looking at the character, and the blue are the non-targets. And you'll see that you get a nice strong peak around 300 milliseconds after the stimulus was presented. And on the right-hand side is the same thing, but the uncleaned version, the raw version. And so we're using some clever little methodology around blind source separation to pull out the targets. And of course, we're trying to do this in real time as well. So we can do that, and we can end up with a really strong recognition, when the right character is lit up. So essentially, another way of doing this is, instead of creating this so-called recognition response, P300 response, we can take LEDs and we can flash them. If we flash the LEDs at 12 hertz, you look at those LEDs, very easily on the visual cortex, we can pick up a 12 hertz activity. If we give you an LED flashing at 14 hertz and you look at that, then when you look at the 14 hertz, we pick up 14 hertz from the visual cortex. So if we put an LED on the left at 12 hertz, an LED on the right at 14 hertz, we can tell if you're looking at the left or the right simply by looking at your visual cortex. So we could come up with this sort of like binary system, as I've shown here, zeros and ones if you're looking at left or right. And it's quite a strong response. And again, all you need to do is look at it. The downside is that flashing LEDs is not nice. It's not comfortable. It becomes very tiring after a while. Plus also, if you're doing this on sick individuals, especially people with brain injury, there's a risk that you might be going into the area of epilepsy and triggering seizures and all that type of side of things. However, it does work. So this is what it looks like. This is, they call steady state visual evoked potentials. So we have this so-called virtual button flashing at 12 hertz. This is the activity that we see on the electrode over the visual cortex at the back. And you can see a very nice clear peak at 12 hertz. Now you might say, oh, what's this at 10 hertz? Well, there's a very natural phenomenon in the brain that so-called alpha activities appears over the visual cortex at around 10 hertz. And that's very natural. And it gets stronger when you close your eyes. So that is a normal alpha activity, and it's this response that we're trying to look for. And if we flash something at 16 hertz, say, that's what the response looked like. And again, you get a very nice clear peak at 16 hertz. So a really strong way of detecting one over the other. This is another video of a lab in China, and you can just see those little, that's basically a keypad, and you can see them all flickering away, and they're all flashing at slightly different frequencies, 12, 14, 16, 18, so on hertz. And to type that number, all the user has to do is just look at those flashing buttons. Again, all we have are electrodes over the visual cortex and a relatively small EEG amplifier, a 4-channel EEG amplifier. So now the guy is going to type on that virtual keypad simply just by looking at the characters. And this is the sort of the computer side, which is deciding which of the keypads you're looking at, which of the buttons you're looking at on the keypad. So you'll see him type it now.
0, 1, 3, 8, 1, 0, 8, 5, 3, 9, 0, 7, 4.
So you can see basically that in a very simple way, with very little brain effort, if you like, which is different to the self-paced way of doing BCI, you can also get a decent response. But again, it's a relatively limited, very sort of discrete binary type of responses that you can get. But, you know, good, strong responses. So again, I said, being an academic, you get to do fun things. And one of the things I thought of one day was a little fun experiment where I said, let's try and do brain-to-brain communication. So something, I think of something on this end, I transmit it somehow to another person, and from that other person's brain, we pick up that something. I mean, that would be absolutely brilliant. And essentially, what I did was I basically took these two types of paradigms and put them end to end. So basically, I had a PhD student at home with an EEG system with the 2 channels, and he was using the motor imagery self-paced method, which is basically imagine doing this for a 0 and imagine doing that for a 1. And so you sit there and you imagine doing this and that, and we can get a bunch of 0s and 1s. At the other end, we have someone else, and yes, you guessed it, it's my daughter, and she's sitting there looking essentially at a computer in our own home with a bank of LEDs, and those LEDs will flash at 2 frequencies. They'll either flash at, I don't know, 12 hertz or 16 hertz. And if it's 12 hertz and we detect it, it's a 0. And if it's 16 hertz and we detect it, it's a 1. And then all we did was very simply, through the internet, we took the 0s and 1s that the motor imagery guy was generating and flashed the LEDs at the 2 different frequencies based on those 0s and 1s. And so the 0, 1, 1, 0, 1 sequence you see there coming out of the brain of the first person, we picked up from the brain of the second person. Oh, and I tell you what, we did this experiment, we got a little video, and the media loved it. This is one of the things about BCI is the media. And this is part of the reason why I'm having this philosophical discussion, and we'll talk a bit about the future now, because it's one of those areas which has lots of potential repercussions. So you do anything like this, the media are all over you, and you start receiving letters. And I started receiving letters, some of them written in green ink, which is a bit scary, and I could talk about that later. So this is how the Times of London showed it, essentially the same figure that I had over there. I'll show you very quickly now a little video where on the motor imagery side, the 1011 is going to be sent and at home. So there's my student. You can see he's imagining a 0 or 1, and the 1 is what he was imagining. That gets sent home. You'll see the flashing at our home, and that's flashing at a particular frequency. And from the visual cortex, we pick up the 1. And then you do a bit of handshaking and the whole thing starts off again. So you just repeat that. What are the observations? A, it's very, very slow, because we need to make sure we pick up a strong signal at one end, and we need to make sure we pick up a strong signal at the other end. And I think most crucially, my daughter is not sitting there going, ooh, 1, 0, 1. No, she's not. She's completely unaware of the 1s and the 0s. We're just picking it up from her visual cortex. You know, she's just part of her brain is just part of the conduit. So yes, technically it's brain-to-brain communication. And in fact, I gave a talk in Chennai, and the following day in the Times of India, I was declared the father of telepathy. And you know what? I'm quite happy to go with that. So you heard it here first. If you hear about telepathy, I'm the father of it. But you know, jokes apart, it is brain-to-brain communication, but there's a crucial element which is missing here. And the crucial element is that there's no sort of recognition side of this. And why is that? Well, I could, if I really, really wanted to, and my wife let me, I could have drilled holes in my daughter's head and put electrodes in a particular part of the brain and stimulated that part of the brain with 0s and 1s. And I could have elicited responses. It's a known thing. You know, surgeons do that all the time when they're doing brain surgery. But of course, you know, I sort of draw the line at drilling holes in my daughter's brain just for a throwaway experiment. So I had to use the next best thing, which was stimulate the brain through the senses. So that's what I'm doing there. I'm stimulating the brain through the senses. So is it telepathy? Clearly it isn't. But, you know, Times of India said it is, so I'm not going to complain. So future. Let's now start to bring all of this together and ask a few questions. Essentially, neuroimplants happen. They're doable. They've been doing them in animals for years. This is the BrainCate system, like I say, and that particular chap there, you can see he's got a breathing tube. He became very good at using this particular brain implant, and he could move a cursor on the screen essentially just by willing it to move, as I was saying earlier, through these imagined movements. You'll see that the implant is very tiny, so it has to be sitting in a very specific area of the brain. And of course, you have to operate to get that in there. Now, the downside is that this is usually used on people who are very sick. In this particular case, this person actually was, I think he was stabbed, and he ended up complete paraplegic, you know, through a stabbing incident. And he was very sick. And I think it turned out that I don't know how many months later, this system had to be removed because he had other medical complications, you know, and this was getting in the way. So these systems at the moment tend to be used on sick people. And there are considerations to using this on sick people. And of course, it begs the question, should we be using this on non-sick people? You know, ethics, all that type of thing starts creeping in. There are other labs working on other types of BCI. So this is a wireless BCI system, and it's being used to synthesize speech. So this is someone who's had injury, brain injury, which has affected speech. And this particular BCI is stimulating it's picking up the speech regions and figuring out the words that you wanted to say and saying them for you, essentially. And the good thing about this is you don't have to have a socket sticking out of your head. You can have an antenna subcutaneously and a receiver coil, similar to the cochlear implants. So you got Wi-Fi, although you get the whole different meaning to someone hacking your Wi-Fi in that type of scenario. Also, cochlear implants, I mentioned them. cochlear implants are a good way of stimulating a very specific part of the ancillary systems that then go and stimulate the brain. So cochlear implants allow people to hear who've never heard in their life. We can stimulate the cochlea and create hearing, essentially. So it's been happening for a long time. And in fact, in the UK, children who are born deaf, who cochlear implants are suitable, they will get implanted as young as 6 months because it's a system that works. So, we can stimulate parts of the brain. There are projects around the world where we're stimulating the brain for vision. So this is the Boston Retinal Implant Project, where a little camera mounted on the glasses takes the signal, does some signal processing, transmits it to the retina, and stimulates the optic nerve so that you perceive the image through this, manipulation of the image. So again, we're stimulating the senses, but more directly right at the brain side of things. I should have said that I have a bit of a gory picture there, but this is just to show you that, as I say, interoperatively, neurosurgeons routinely stimulate the brain. In fact, most times when brain surgery is being performed, the patient is awake, just a local anesthetic, and all those little electrodes you see there is the surgeon is stimulating parts of the brain, making sure that he knows where vision, hearing, speech, motion are. In fact, you can see little labels there. And the reason he's doing that, the surgeon, is that they don't want to, if they're going to remove part of the brain, they want to make sure that they steer clear from, very important parts of the brain. So stimulating the cortex is doable, very doable, and it's done quite routinely, and it's been done for a while. Here's another system. It's called DBS, or deep brain stimulation. And for a particular disease such as Parkinson's disease, this implant, which is a really deep, it goes right down into the subthalamic nucleus, and it stimulates that part of the brain, and it has a dramatic effect on Parkinson's. So here's an example video. Here's a person showing you that they have tremor movement before the implant, with the implant switched off. Now when they switch the implant on, look at the difference. So this implant is stimulating a very specific part of the brain. Essentially, it's a square wave. It's just blatting that part of the brain with a signal. On the left, you can see the person barely able to walk properly because of the tremor, and on the right, completely walking. So why am I showing you all of this? I'm showing you that it's possible to read signals. It's possible to stimulate. And of course, if we really wanted to stimulate without drilling holes, we could. There's something called transcranial magnetic stimulation, TMS. Essentially, it's a great big core of wires, a coil of wires, excuse me, that when you generate an electric pulse, it generates a corresponding magnetic field. And that magnetic field, when you hold it next to the cortex, generates little eddy currents in the cortex, and you can stimulate that part of the cortex. So we can stimulate the cortex without having to drill any holes. But of course, this thing looks like it's huge, because the magnetic field that you're generating has to be quite large, which in turn means we need a quite large electric current. So not exactly wearable and portable, but it's there. And of course, last and not least, Elon Musk has been busy. His company Neuralink has created this little implant, which he calls a small wireless battery-powered implant, unseen from the outside of the body. In other words, it's implanted, it's battery-operated, it's wireless. It does all of the things that we need to make it usable, unobtrusive. And Elon Musk says that it's like a Fitbit in your skull with tiny wires. And in fact, it could have up to 1,000 wires. Now, that's a lot. It is a lot. Usually we're talking in the order of 60 or 100. But bear in mind that the brain is made up of, I don't know how many billion of neurons. So 1,000 is a big number, but it's tiny in comparison to the brain. And the reality is that if we really wanted something like this, we want to have a whole bunch of these all over the brain, all picking up information from different parts of the brain, because we know motion sits here, reason sits here, memory is there, visual cortex is here. So where something is in the brain is really, really important. So this is a really strong positive step in the right direction. And in fact, at the end of last year, they did a live demo where they basically showed a pig which has one of these implants. And it shows you that this is the sort of output that you get. And it says here that the electrodes record the activity of somewhere between 0 and 4 neurons in the brain, each electrode. 4 neurons is a pretty small number, when you think that it's the billions of neurons acting together that give us, this higher thought processes. So it's a good step in the right direction, but it's a very tiny step in the right direction. So I'm reaching the point now where I'm going to start closing up. So the future. Can we do brain-to-brain communication? Let's start there. Well, BCI, from a concept point of view, it happens. We know it can happen. We can use implants safely. It's been shown quite a lot. There are some risks, but we can manage that risks. We can do wireless, we can do low power, we can do implants. All of those are a reality. So from a technical perspective, there aren't any issues with the implant side of things. We realize, of course, that if you want to do brain-to-brain communication, we need to stimulate. And I've shown that we can do that already through the cochlea, through the retina. Surgeons do it all the time. So again, from a technical perspective, we can stimulate all sorts of parts of the brain and have responses. And of course, brain-to-brain has been shown in principle. I've proved it. I'm the father of telepathy. And, so as a principle, we can show that we can do something like this. And of course, there have been other papers where there was scientists in the US who had rats implanted and a scientist in Brazil. And the rat in the US was feeding and was influencing the feeding of the rats in Brazil by they were taking activity from a particular part of the rat's brain and stimulating the same part of the rat's brain in Brazil. But those are rats. And whilst that's brilliant, and we can do that to rats, rats don't have, or we say that they don't have the higher order thinking that we have as humans. So we can't really take the rat's word for it. We're having to visually observe these. So the question now is, do we want brain to brain? Is reading from the brain and stimulating the brain something that is useful? Stimulation sites, as I said, and the patterns that we need are very, very complex. And the reality is that if we want to do this where it's foolproof, it's invasive because we have to drill holes, we have to open the skull, we have to put lots of electrodes in places. Clearly, there are severe ethical implications. A lot of research that happens at the moment happens in patients who are, for example, undergoing surgery for epilepsy. And whilst the surgeon is doing surgery, they will get ethical approval to put some electrodes where in the brain so that they can do some BCI type analysis. But the problem there is that you're limited to the area where the patient has their epilepsy, which is where the surgeon is operating. They can't just pick and choose where they're going to place the electrodes. So there are ethical implications. Also, believe it or not, there are privacy and security issues. If you have a wireless system and a wireless system which is wired, quite profusely in the brain, you have to be very sure that the security element and the privacy element of that communication system is rock solid. Because like I say, I received letters from very anxious people, some people who are quite scary to receive these letters from them. And a lot of them, the biggest concerns are the governments of this world controlling the brain, the religions of this world controlling the brain. And whilst conspiracy theories apart, you can see that it's not to be taken lightly, the privacy and the security side of things. And I think the last line sort of says it all. What is the long-term physical and mental health issues with having implants, where a lot of people, including Elon Musk, they talk about augmenting the human. So it's not just about allowing someone who's never moved their arms to move them or never heard to hear. It's about people who have all of their faculties and giving them, something else. What are the long-term physical and mental health issues with that? Completely unclear, bound to be issues that need to be addressed. So this is my last slide. Essentially, we can get information out of the brain. We can implant, so from a technological point of view, no problem. We can stimulate the brain via the senses at least, and we could also do it via implants. Questions, though, which I'll leave there. Do we really want to do this? And how will we use it and why? So these are just questions that, there may be answers to them, but I'm going to leave them there. And the last slide that I have is a wonderful cartoon that I saw in a newspaper somewhere. And it, again, a whole new meaning to BCI. One more reason to be excited about the next millennium, telepathic telemarketing. That's scary. Thank you. That's my talk.
Thank you, Christopher, so much. That was a fantastic talk. I want to jump right into questions, and I see that we're about 5 minutes to the hour, so I want to prioritize folks who might have to leave. If you don't want to ask your question directly, go ahead and just drop it in the chat. The first question that was dropped in of the Parkinson's slides you were showing, just simply, do we know why DBS helps?
Actually, you know what? It's very much a sledgehammer approach. We know that there's some sort of a pacemaker type signal that we're trying to get in tune with. But the reality is that it's a square wave, and the frequency and the amplitude are tweaked, and observe the outcome. It really is very, very crude. We know that we're trying to, essentially it's like having beats and you're trying to get everything in synchrony, but the finer detail, we don't really know. And also, I don't know what the percentage is right now, but it's only in a percentage of people that this system will even work. There are some people where you'll try it and you will just not get it to work. And that's because they don't really understand what it is that's happening. But they do know that if they basically, it really is a sledgehammer to crack a nut. You've basically taken a region of the brain and you're just blatting it with an alternating current, which is essentially masking the effect of the tremor, essentially.
Awesome, thank you. We've got one here, sort of a multi-part question. To what extent is the bottleneck in advancing BCI, 1, discovering new brain signals, 2, inventing new measurement devices, 3, better signal processing, or 4, developing new use cases?
Right. I think signal processing, we already have it. The only thing that we have to deal with is this, what I mentioned earlier, the so-called curse of dimensionality, because basically, depending on the complexity that you want, the numbers start to increase. So then you have an issue of being able to process everything in real time, to catch up. But in reality, we already know quite a lot about different parts of the brain lighting up under different conditions. And the responses that the brain works in are in the orders of hundreds of milliseconds, 50, 60, 100. And of course, the higher the milliseconds, the higher the thought process. So in the first few milliseconds, it's at the base level. And in the hundreds of milliseconds, you're at the higher thought processes. And so because we're dealing with hundreds of milliseconds, other engineers around the world are dealing with megabits per second in transmitting information around the world, etc. The brain is very slow in that respect. So from a technology point of view, I don't think it's an issue. I don't think it's a signal processing. I don't think it's only a signal processing problem. We know a lot about the brain already. The question is, though, how do we take that and try it and deal with these ethical questions? Do you ask for a volunteer who's going to have their brain, fully implanted with a whole bunch of electrodes, where the risk of infection, et cetera, is very high? it's a real issue. It's a real question.
Evan, did you want to ask a question?
Yeah, happy to ask it out loud. So Protocol Labs is in the business of trying to design and build digital infrastructure. And like one of the clearest examples is trying to build a global, secure, distributed storage protocol system mechanism. Could frame it multiple ways. And I'd be curious, given that there are types of data that you might want to, like, I guess one of the things that one of our projects, it makes it much easier to connect two computers directly to each other because the internet has been optimized for this client server architecture. And it's non-trivial to connect one laptop directly to another. And when we're trying to build and expand and future-proof and design understanding what future capabilities should be, I'd be curious if there's anything that you think we should be headed toward to accommodate BCI privacy or ethics or user experience or security.
Yeah, I mean, it's a tough one because obviously, clearly they need to be there. It's obvious, I think, the security aspect of it, the privacy aspect of it. I'm going to try and sort of spin it on its head a bit. When I hear Elon Musk talk, I hear him talking about things like we'll be able to download memories from someone's brain. The implication being that we're from the outside probing and sucking information out. There's nothing at the moment that allows us to do that. It has to be generated from the inside, going out. And so security in that direction, security in that direction isn't the issue. It's if I choose to get information out, how can I be sure that that information goes to the intended, end use? And the intended end use may be controlling something, I'm a paraplegic and I want to control the lighting or the temperature in my house, or it may be I'm gaming in some really fantastic, super futuristic game, and I want that information to go wherever the gaming infrastructure needs to be. So, very, very different sort of scenarios, but I'm guessing, and it's not really my area, but I'm guessing the security aspect of it shouldn't be that different. But it's not my area.
Yeah, I think usually in the security world, this gets solved with like some amount of trust, either some trusted entities that can give you trust that you're communicating with who you think you are, or you can set up some protocols to try and create that trust. But it's like knowing who you're talking to is a quite difficult problem.
Yeah, I think it becomes then a question of implications. What are the implications of the information getting out there? If it's a question of, I don't know, it's my bio-identity card, therefore my identity is stolen, then clearly that has, very, very strong repercussions. And also, if what I'm trying to do is to move my wheelchair to stand me up and somebody hacks and throws me on the floor, there are other type of implications. And I think it's not talked about enough at all. It's not a technical discussion, I guess, is what I'm trying to say. It's more of a protocol type of thing, isn't it?
So there's another question that I'll read, and I folded into a question of my own as well. So the question in the chat is there any possibility of using signals from sub-vocalization, any different use case to quote unquote real BCI? And the question I had, which is loosely related, is just what areas of brain activity other than the sensory motor area, a lot about visual cortex and motor functioning, have been used to have been studied in BCI?
Yeah. So in terms of subvocalization, the short answer is if there's muscle, and for subvocalization there's muscle, even if it's very tiny, muscle is like 1,000 times more measurable than EEG. So that if there's muscle, you measure the muscle. So you don't measure up here, you measure wherever the source of the muscle is, because that's going to be a stronger, clearer, you can extract information out from that no problem. If you can move your tiny little finger for a yes, no, I'd prefer doing that than doing EEG, because I can get a much better response from here than I can from up here. The effort involved is very different. So from that point of view, if there's muscle, you go with the source of the muscle. On the other side, clearly there have been motor cortex is the biggest one, because the imagined movements. There are people that have experimented with imagine a scene. So remembering a scene. So they tell people, like, imagine you're floating through your house and you're visualizing scenes which are familiar to you. And that essentially is you're invoking memory type responses. And the idea there is that you pick up patterns, and we learn what those patterns look like. And every time you invoke that particular memory, that particular response, we say, you must be visualizing that. So memory is one. As I showed there, you can tap into things like speech and vision at the higher order levels. So not at the point where I'm moving the muscle to create speech, but at the point where I'm thinking of the word cat. I'm thinking about saying the word cat or the word book. So at that higher level is where they're trying to extract information. But it tends to be all very, very focused. Yeah, I don't know of any widespread approaches where basically they say, we're going to put a whole bunch of electrodes here. We're going to get some really wide varying signals, and we're going to try and make sense of them. The reality is that we can't put that many electrodes. You can do it in animals, but animals don't talk to you, so you can't sort of figure out what's going on with them. So it tends to be very focused. And I would say 90% of BCI, figure out of my head, is probably motor imagery.
Great. Yeah, thank you. Next question in the chat is, do you believe the outgoing can be produced and exploited as part of an enhanced interrogation procedure? And if not, why not?
That's a very interesting question. I've seen studies where you talk about subliminal type of activities, where you show someone images and you slip in subliminal messages, and the brain does. You can pick that up. You can pick that a person is having an emotional type of response to a particular image. We've shown, for example, where if you show someone faces, happy faces, sad faces, angry faces, we can tell the response that you're getting, happy, sadness, etc. So the reason I'm saying this is I think it's probably doable to trick someone into giving you a response that is measurable. So it's probably it's probably doable to show someone a series of stimuli where if you get a positive response, it's because that person has associated that stimulus with a particular type of response. It's not we know the center of the brain where truth and lie exists. It's not that. It's that the brain will respond, and you can't hide that, and we piggyback on top of that response the fact that we created a particular stimulus. Very long-winded way. So essentially, if you I don't know, you were witness to something, and you you witness someone killing someone, we show you a whole bunch of pictures, and when you see the picture of the killer, we get a response. Now, it's not that simple, because there are things that you can do to mask, for example, people who can beat the lie detector, that type of thing, but I think we're not there yet, but I think it's definitely a possibility.
Next question, I guess I might reframe this. Well, the question itself is, have you considered fail and such constructions to ensure you can always get out, which is to say, just sort of cut off any type of brain stimulation that's happening? And
sorry, I don't understand that.
Should I try to explain it?
Yeah, if you want, then that's great.
Yeah. So my point is, like, assuming you would actually do stimulation on at a point where you get information into your brain which you really don't want, and you realize it like too late, basically.
Yeah.
And so now the question for me is like, how do you make sure that you can still get out of it as fast as possible? Because I assume that it's basically the same if you look at the video, right? You trust the source maybe, but you don't know the video's content until you've actually watched it. And so I imagine this to be in a similar situation, and I have the, fail safe here. I can just close the video, hopefully, or run away. And so the question is, how can I have something like that in my brain, basically, to stop that? And then the other question is, what if the content simulates me that I have a fail safe, but the fail safe is fake? Obviously, gets into the recursive problem.
Yeah, it's a very good question. I think that any type of interaction that we have is going to be technology based. So there's going to be some type of technology, whether it's implanted or in your pocket or whatever, that technology is there. So it's as good as the fail sales of that technology. Now it could be as simple as you switch it off, you disconnect it, you whatever the terminology might be. Yeah, but it does depend on the end use. So, for example, if you are, I deal more with sick people rather than people using this in a sort of a leisure type environment. If you're in a situation where you can't move a muscle, and this is you're dependent on this, then probably that could be exploited, and you probably won't be able to react because your reactions are limited, if you see what I mean. But I would imagine that in a situation where this was working in a sort of an enhanced human being type of approach, you can always intervene and create a block. Any stimulus will not have a long lasting effect. You're not going to, it's not like an EEPROM and you're going to overwrite the ROM sort of thing. It's a momentary stimulus. And the effect is not long lasting.
Yeah. Thank you.
I'll hop in with just one of my questions. With actual implants, what are the materials degradation concerns or timelines?
Yeah, one of the things I didn't mention this, but it is a problem, is scarring. So the body doesn't like foreign objects in it. And so there's a lot of research on having materials that aren't rejected by the body. Great. But then you get scarring forming over the site of the electrodes. Usually they use these tiny little arrays, which are like, 64 or 128 electrodes in a grid. And the body starts growing scar tissue over it because it doesn't like foreign bodies there. And what you find is that after weeks or months, the number of electrodes starts to drop out. And one of the reasons why they have a large number of electrodes is to have that element of redundancy. And you could end up with a situation where it might be weeks, it might be months, that the electrodes become useless because of scar tissue forming and it creating a barrier. So there needs to be some element of consideration for that side of things as well. I don't know Elon Musk's system, how well they've addressed that. It may well be that they've, from a materials point of view, they're coming up with materials that are better accepted and all that sort of thing. But as it stands, there is deterioration. As it stands, after a while, you need to remove the implant because it's useless. What are the clinical timelines that we have in terms of maybe the longest implanted BCI technology that we've been able to study so far, whether it's human or animal? I think in animals, they tend to be in the order of many months, not years. A lot of times, I think the implant is not useful anymore. The sad side on the animal side is that a lot of times they end up sacrificing the animal anyway because they want to look at the brain and look at the effect of the brain. So it's a completely different story there. In humans, again, I don't know of any. The number of people that have been implanted have been very few, for starters. And the few that I'm aware of have had their implants removed after a while. mainly because they're ill, they're sick people, and the implant is getting in the way of their debilitating, disease, and it got removed. So I don't think that the evidence is strong that this is something that you can put in and forget. I think the evidence is that as it stands at the moment, it got a lifetime to it, this implant. Which is why
Awesome.
I don't use implants. I use scalp electrodes because
Right.
they fall off when we put them back on again. The downside is that we have really crap signals to work with. But,
Thanks for joining, everyone. Our next talk is April 13th at 1700 UTC from Dr. Rohin Shah, who is a research scientist on the technical AGI safety team at DeepMind. His talk will give an overview of the current state of and directions for AI alignment. If you're watching on YouTube, please remember to like and subscribe and share this video. If you want the Zoom link to join future talks, join our mailing list in the footer at research.protocol.ai. We also send out quarterly newsletters and announcements about research funding opportunities. Thank you for joining. We will see you next time.